I'm Melissa, and I'm an 8th grader at Weindruch Middle School, and we're doing a project called One Small Step. One Small Step is an energy / NASA project. We did tons of research and had to choose an idea from either energy or NASA and figure out how to make it better.
First, we chose to make a watering system for a test case. At the last minute, they decided they didn't want a watering system. So then we had to research another project to do, and we found that Mr. Udi wanted a more efficient and easy watering system for his students' greenhouse.
For a couple of days, we researched and thought of ideas. We talked to Mr. Udi and Mr. Codwell. Mr. Codwell is the custodian supervisor at our school. We asked him for advice on our project.
He told us that we couldn't use a hose connected to the school hose spout because it would waste too much water. Then he suggested a rain barrel. We talked to Mr. Udi about our idea for a rain barrel.
He said that was fine. He did end up getting a rain barrel for us, but the initial plan was to build our own. At the time, we weren't really sure that the rain barrel was ours, because there had been other groups working on the greenhouse.
I asked him if it was ours to work with or was for another group. He said it was for us to use. So we explained our idea to Mr. Udi, and he said it was fine. Our plan was to hook a tube up to the rain barrel and have it hanging through the window.
Problem. We thought that there was going to be enough pressure to push the water from the rain barrel up the tube and out through the sprayer to then water the plants in the greenhouse. We had to change our idea yet again. We decided to leave our prototype as a manual sprayer.
Our finished prototype has a rain barrel, a plastic tube we use as a hose, and a sprayer. To use it, first you have to make sure the water fills the barrel to at least the second tape mark of the tape mark.
As you can see, ours isn't right now, which means we have to add more water for it to actually work.
Step 1. Identify the problem. State the problem clearly. Can we create an easy-to-use watering system for Mr. Udi's students? Step 2. Identify criteria and identify the conditions that must be solved for the problem. We have to find and achieve a nice watering system for their plants that is easy to use. Identify anything that might limit the solution. The cost of a renewable watering system might be too expensive. The watering system itself might be hard to use. Step 3. Brainstorm possible solutions. Consider what others have done to solve the problem and conduct prior research. Mr. Udi's students came up with a Tupperware with holes for straws. Every so many days, they would pour water in the Tupperware, and the straws would point to a certain plant, so the plant would get water. Some solutions we came up with: we are going to make a nice water system that we researched, which is efficient and easy to use. Step 5. Build a model or prototype. Write a detailed procedure for building the model or prototype. Get everything needed for the prototype. Build a prototype as soon as we have materials for it. Once we figure out if it works or not, we will go on either building a new and improved prototype or the actual model. And things we would use, I guess, would be hooks, PVC pipes, misting nozzle, hoses, a greenhouse, and a water barrel.
Our conclusion. Our hypothesis was we think it will have to be 10 inches to make our system, 10 inches deep to make our system work. Our hypothesis was incorrect by only 1 inch. The water at least had to be 9 inches for water to come out of the hose. It can be 9 inches and up, but nothing lower than that, otherwise our watering system will not work. Experiment 3. How long will it take for the water to come out of the nozzle? Our hypothesis was, we think that by the time we turn the water on, it will come out as fast as a normal hose. What really happened? We realized that it didn't come out as fast as we thought it was going to. So we timed it. And for how long it takes from the water to come through the hose and out of the mister was 23.11 seconds. Our hypothesis was, we think that by the time we turn the water on, it will come out as fast as a normal hose. Our hypothesis was wrong again. A regular hose hooked up to house comes out a lot more faster than our hose that was hooked up to the rain barrel. It takes 23.11 seconds for the water to come out of the hose we have. Another learning target we used was explain how energy can be converted from one form to another. It's important to accept that energy is an abstraction. It's not some sort of invisible stuff that flows from one object to another. Another learning target is explain the law of conservation of energy. The law of conservation of energy states that the total amount of energy in a system remains constant. It's conserved. Although energy within the system can be changed from one form to another or transformed from one object to another, energy cannot be created nor destroyed, but it can be transformed. The last learning target we used is utilize technology to improve energy conversion. Energy conversion is the process of changing one form of energy to another. We utilize technology to improve energy conversion because we researched how a rain barrel could help with our project, and we researched energy.
One topic we took for notes for our project is the greenhouse. For greenhouses, there are many different types. There are hoop houses, arch structured or framed that provides cover, usually for overwinter plant materials or for starting or late spring crops early in the season. The typical ones do not have heating or cooling systems. And then the next topic is rain barrel. Ready-made ones are $89 to $135. And then rain barrels conserve water and help lower costs. About 1,000 gallons of water during the summer months.
We took notes on the specific watering system for every kind of plants. There are many kinds of watering systems. For example, there is a drip irrigation system. These expose roots to direct supply of water. They release water in slow and steady fashion. They're small. They're the size of a quarter. The location on the ground is in rows. It provides control. It eliminates the probability of water running off. Another kind of watering system is a soaker hose. A note for this is sweat water along the entire length. A traditional automatic spray system, it pops up spray heads. It can be adjusted by spray full size, half size, and quarter size. Another kind of system is a rotor system. We are the Water Minions, and this is our logo. We chose this logo because we all love minions, so they represent us, and we called it Water Minions to symbolize our project of making water systems. We looked at Home Depot for the materials, and we printed pages out on like what we think we would need. And the blueprints are back here, and we also had to get the blueprint signed by our teacher, which we did. And as you can see, we had to change the blueprint many times because we changed our project. So that is our binder, and thanks for watching. As you can see, we had a binder for all of our papers and materials and things that we needed for the Water Minions. And as you can see, it still says Tuskies, which is incorrect. But every day we had a checklist to complete, and so we knew like what we had to work on that day and what needed to be finished and what was finished. We also had a calendar for the whole project. We worked on it from the second week in April to the 16th of May, I think. And this is just like the calendar that we used to like track what we got done and things. And we also put some reflection logs and how kinetic energy can affect our project. And this is how we were going to build the watering system. We looked at